The Rhine River in the spring of 1945 represented the final, formidable gateway into the heart of Nazi Germany. For the Allied armies fighting their way east from the Normandy beaches, it was the last great natural obstacle, a wide, fast-flowing moat that the retreating German forces had turned into a nearly impregnable defensive line. The German High Command's strategy was brutally simple: destroy every bridge across the river and fortify the eastern bank with artillery, machine gun nests, and determined infantry. They knew the Allied playbook for river crossings relied on the methodical, time-consuming construction of pontoon and Bailey bridges, a process that could take days and would present a massive, stationary target for their guns. They were confident they could turn the Rhine into a killing zone, bleeding the Allied advance white and buying precious time to regroup for the defense of the fatherland. The twisted, skeletal remains of the bridges at Remagen and other potential crossing points stood as stark monuments to this strategy. The Allied High Command faced a grim calculus. A direct assault crossing would be incredibly costly, and the delay in building bridges could allow the Germans to solidify their defenses, potentially prolonging the war for months and costing tens of thousands of additional casualties. They needed a miracle, a way to get massive armored forces across the river, not in days, but in hours. What they got was an unassuming 45-year-old American engineering officer from Nebraska named Lieutenant Colonel Jack Templeton, whose radical and heretical idea was initially dismissed as the dangerous fantasy of a madman. Jack Templeton was not a product of West Point. He was a civil engineer who had spent the pre-war years designing bridges and dams across the American Midwest. He was a practical man, a problem solver who thought in terms of physics, load-bearing capacities, and material strengths, not military doctrine. While the senior engineering brass at Supreme Headquarters, Allied Expeditionary Force, SHAF, were meticulously planning for the massive logistical undertaking of shipping countless Bailey Bridge components to the Rhine and assembling them under fire. Templeton was looking at the problem from a completely different angle. His moment of inspiration came not from a textbook on military engineering, but from watching a column of Sherman tanks being loaded onto a landing ship, tank LST at a port in Antwerp. He saw the immense, robust vessels designed to cross oceans and disgorge heavy equipment directly onto hostile shores, and a seemingly impossible question formed in his mind. What if the bridge didn't have to be built from scratch? What if they could be the bridge? The concept was deceptively simple in theory and breathtakingly audacious in practice. Templeton proposed lashing multiple LSTs together, side by side, to form stable, floating platforms. These platforms would then be connected end-to-end using a system of heavy-duty, custom-designed hinges and locking mechanisms, creating a continuous, floating roadway across the river. The deck of the ships would be covered with a layered roadbed of timber and steel Marston matting, the perforated steel planking used for temporary airstrips. He called it the Composite Floating Bridge, though it would soon be nicknamed Templeton's Folly by its many detractors. The advantages were revolutionary. Unlike a Bailey Bridge, which could take 3 to 5 days to assemble its hundreds of components under ideal conditions, the LSTs could be pre-positioned and assembled into a bridge in a matter of hours. Their inherent buoyancy and massive size could support the weight of the heaviest Allied tanks, including the new M26 Pershing, which strained the capacity of even the most robust traditional military bridges. Most importantly, the bridge was mobile. If one crossing point became untenable due to enemy artillery, the entire structure could be disassembled and moved to a new location. A tactical flexibility that was unheard of. Templeton drafted a detailed proposal, complete with schematics, load calculations, and a phased implementation plan. He submitted it through official channels, believing the sheer elegance of the solution would be self-evident. The response from the senior engineers at SHAFE was a wall of unified, derisive opposition. A specially convened review board, comprised of colonels and brigadier generals with decades of combined experience in military engineering, systematically dismantled his proposal. Their objections were numerous and, from their perspective, entirely valid. The hydrodynamic forces of the Rhine's powerful current on the broad, flat-bottomed hulls of the LSTs would be catastrophic. They argued the bridge would twist, buckle, and be torn apart. The process of aligning and connecting multi-thousand-ton vessels in a fast-moving river was a navigational impossibility. The ships would collide, crush the smaller tugboats, or be swept downstream. The structural welds of the LSTs were not designed to handle the immense bending and torsional stresses of being part of a rigid bridge system. The hulls would crack and the ships would sink, taking men and equipment to the bottom. The logistics of providing the necessary timber, steel, and specialized connecting hardware were a nightmare that would divert critical resources from the proven Bailey Bridge program. The final verdict from the head of the board, Brigadier General Arthur Thorne, was delivered in a terse, dismissive meeting. "Lieutenant Colonel Templeton," Thorne said, his voice cold and sharp, "this proposal demonstrates a fundamental misunderstanding of naval architecture, fluid dynamics, and combat engineering. You are attempting to use a ship for a purpose it was never designed to fulfill. This is not innovation, it is recklessness. I will not risk lives and valuable naval assets on this fantasy. The proposal is rejected. You are to return to your unit and focus your efforts on supporting the standard bridging operations. That is an order for a lesser man. This would have been the end." But Jack Templeton was a stubborn Midwesterner, a man whose faith in physics and practical engineering outweighed his respect for rank and tradition. The rejection only solidified his conviction. He saw the board's objections not as fatal flaws, but as a list of engineering problems to be solved. The current U could use a system of multiple heavy anchor lines set at precise angles upstream and downstream, combined with the power of the LST's own engines and auxiliary tugboats, to create a dynamic stabilization system. The connection problem. You could design a universal joint mechanism using massive forged steel pins and reinforced I-beam cradles that would allow for limited movement while maintaining structural integrity. The hull stress. You could install internal bracing within the empty vehicle holds of the LSTs, creating a reinforced spine that would distribute the load. He began working on the revised designs in secret, during late nights in his quarters, using whatever scrap paper and drafting tools he could find. He was a man possessed, driven by the chilling certainty that the established bridging methods would lead to a bloodbath on the banks of the Rhine. His breakthrough came from an unlikely source. A young, bright captain named Richard Shaw, who had served as the recording secretary for the review board, sought Templeton out privately. Captain Shaw was an engineer from MIT, and while he understood the senior officer's conservative stance, he had been secretly fascinated by Templeton's outside-the-box thinking. "Sir," Shaw said, finding Templeton alone in a makeshift officer's mess, "I believe your concept has merit. The generals are fighting the last war. You're trying to win this one. I have a contact in the Navy's Bureau of Ships. Let me get you the complete, classified structural specifications for the LST hull. Your calculations are good, but with the actual metallurgical data and weld strength specifications, we can prove the hulls can take the stress. This clandestine alliance changed everything. With the precise technical data in hand, Templeton's revised calculations were no longer theoretical. They were concrete and irrefutable. The LST's hull was significantly stronger than he had even hoped. He redesigned the connection system, creating a robust knuckle joint that could be bolted into place by teams of engineers working from the decks of the joined ships. He refined the decking plan, specifying exactly how the Marston matting would be locked together over a grid of railroad ties to create a seamless, durable road surface. Armed with this powerful new data and a refined, detailed design, Templeton knew he had to bypass the conventional chain of command. Another review board would simply bury the proposal again. He used a personal connection, a cousin who served as a logistics officer on the staff of the aggressive and forward-thinking commander of the U.S. Ninth Army, General William Big Bill Simpson. Templeton managed to secure a brief 15-minute audience with one of Simpson's senior operations officers. He presented his case not as an engineer, but as a strategist. He laid out the diagrams and the hard numbers. "Colonel," he said, his voice steady and earnest, "the current bridging plan will take at least 4 days under perfect conditions. The Germans know this. They have every meter of the riverbank zeroed in by artillery. We will lose a division, maybe 2, just trying to get the first Bailey Bridge across. My composite floating bridge can be operational in under 12 hours. We can have an entire armored division across the Rhine before the Germans can effectively respond. We can shatter their defensive line and be on the road to Berlin. This isn't just about building a bridge. It's about ending this war sooner and saving thousands of American lives." The operations officer, a battle-hardened veteran of North Africa and Normandy, was initially skeptical, but could not ignore the sheer strategic potential. The payoff was too enormous to dismiss. He took the proposal directly to General Simpson, a commander known for his drive and his impatience with bureaucratic inertia, immediately grasped the revolutionary potential. He didn't care about the engineering debates. He cared about results. He saw a chance to achieve a decisive, war-winning breakthrough. His response was characteristically blunt and decisive. "I want to see it work," he growled. "Give Templeton what he needs. He has 1 week to build a prototype and demonstrate its viability. If it fails, it's on his head. If it works, we're taking it to the goddamn Rhine." The following week was a frenzy of controlled chaos. In a secluded, wide section of the Meuse River in Belgium, chosen for its similarity to the Rhine's current, Templeton, Captain Shaw, and a hand-picked team of Army engineers and Navy LST crews conducted the first full-scale test. The operation, conducted under a shroud of secrecy, was a spectacle of raw industrial power. 3 LSTs, emptied of their cargo, were maneuvered into position by a flotilla of tugboats. Using Templeton's newly fabricated knuckle joints and a complex web of anchor lines, the massive ships were painstakingly aligned and lashed together. The sound was deafening, the roar of diesel engines, the high-pitched whine of industrial winches, and the thunderous clanging of steel on steel. Then, the Army engineers swarmed over the newly formed platform, laying down the timber grid and locking the steel matting into place. The work continued through the day and into the night, illuminated by the harsh glare of generator-powered floodlights. Within 10 hours, a monstrous, floating behemoth stretched across the Meuse. The moment of truth arrived at dawn. A single Sherman tank, Its treads clanking loudly on the steel matting, rumbled onto the bridge. It moved slowly, cautiously, reaching the center of the span. The bridge groaned and shifted slightly, settling into the water, but it held. A second Sherman followed, then a third. Then came the ultimate test, a M26 Pershing heavy tank, weighing over 46 tons. As the colossal vehicle inched its way onto the deck, every soldier, sailor, and engineer on the riverbank held their breath. The LSTs visibly settled deeper into the water, and the anchor lines creaked and tightened under the strain. But Templeton's knuckle joints held firm. The Pershing reached the far bank, and a massive, spontaneous cheer erupted from the assembled men. It had worked. General Simpson, who had flown in to observe the final test, stood on the riverbank, a rare, broad smile on his face. He turned to Templeton, clapped him on the shoulder, and said, "Son, you've just punched a hole right through the German line. Get your team ready. You're going to the Rhine." The operation was given the top-secret code name, Operation Thunderbolt. The location chosen was the town of Wessel, a key point in the massive Allied crossing operation known as Operation Plunder. While the world would watch the spectacular airborne assaults and infantry landings, Templeton's bridge would be the true spearhead, the unsung miracle that would turn a tenuous bridgehead into an unstoppable, armored avalanche. The days leading up to the assault were a testament to the immense industrial and organizational power of the Allied war machine. LSTs were secretly diverted from their supply duties and gathered at concealed docks along the Rhine's western bank. The specialized knuckle joints, hinges, and decking materials, which had been frantically mass-produced in army workshops across Belgium, were delivered under cover of darkness. The crews, a unique amalgamation of U.S. Navy sailors who knew the ships intimately and U.S. Army engineers trained in Templeton's novel techniques, rehearsed the complex assembly process until it became a precise, if dangerous, ballet. They practiced in the dead of night, in the rain and fog, simulating the conditions they would face under fire. The pressure on Templeton was immense. The whispers of Templeton's folly had not disappeared. They had merely been silenced by General Simpson's direct order. Senior engineers from Chef, while officially ordered to cooperate, maintained a stance of skeptical observation, convinced they were witnessing the prelude to a catastrophic failure that would clog the Rhine with sinking ships and drowning men. Templeton bore this weight silently, his confidence rooted not in bravado but in the cold, hard certainty of his calculations and the successful prototype. On the night of March 23rd, 1945, the great Allied offensive, Operation Plunder, began. A staggering artillery barrage, one of the largest of the entire war, erupted along a broad front, lighting up the night sky with continuous, flickering orange flashes. The very ground trembled as shells screamed overhead to pulverize German positions on the far bank. Under this cover, British and American infantry began their assault crossing in a vast armada of small boats, battling the swift current and desperate German resistance to establish fragile footholds on the eastern shore. As this epic struggle unfolded, Templeton's flotilla waited in the inky darkness, their engines a low, throaty rumble amidst the cacophony of war. The air was thick with smoke and the smell of cordite. The far bank was a Dantean vision of exploding shells and tracer fire. The moment the radio crackled with the confirmation that the 1st Infantry units had secured a viable stretch of the eastern bank near Wessel, the order was given. Operation Thunderbolt is a go. All units, move out. What followed was a scene of barely controlled pandemonium, a brutal clash of engineering and violence. Powerful tugboats, their pilots displaying nerves of steel, nosed the first three LSTs into the churning, dark waters of the Rhine. Searchlight beams, piercing through the thick smoke, illuminated the surreal spectacle of these ocean-going giants being maneuvered into a river, German mortar and artillery fire, initially focused on the infantry landing zones, quickly shifted towards this new, monstrous target. Geysers of water erupted around the ships as shells landed in the river. Small arms fire pinged and sparked off the steel hulls. The Navy crews, exposed on the decks, worked the winches and anchor lines with frantic precision, their faces set in grim masks of concentration. The first casualty came when a German 80 EMU shell scored a direct hit on the deck of an LST named Courage, killing 4 engineers instantly and wounding a dozen others. Medics scrambled through the chaos to pull the wounded to relative safety, but the work never stopped. There was no time for grief, only for the relentless drive to complete the mission. Templeton was everywhere, moving between the command tug and the decks of the LSTs, his voice hoarse from shouting orders and encouragement over the din. He coordinated with the tugboat captains, adjusting the alignment of the ships against the powerful current. He oversaw the engineers as they, with breathtaking bravery, scrambled to connect the massive knuckle joints, driving home the heavy steel pins with sledgehammers while enemy bullets whizzed past. The decking crews followed immediately behind, laying the steel matting with the speed born of desperation and endless practice. It was a race against time and death. The Germans, realizing the existential threat this emerging bridge represented, threw everything they had at it. Yet, piece by piece, under the hellish glow of fires and explosions, the impossible structure took form. The first 3 LSTs were locked together, forming the initial platform. Then, another section was floated into place and connected. The bridge, a monstrous, ungainly, and magnificent creation, began to stretch its way across the river, a steel serpent defying the very nature of the obstacle it spanned. After 11 hours of Herculean effort, as the first light of dawn began to bleed into the smoke-choked sky, on March 24th, the final section was secured to the eastern bank. The bridge was complete. A temporary, makeshift ramp was quickly constructed, and the order was given for the first vehicle to cross. A lone jeep, carrying a general staff officer, edged onto the steel matting. It moved slowly, the driver's knuckles white on the steering wheel. It reached the center of the span, where the current was strongest, and the bridge swayed and groaned ominously. But it held. The jeep continued, reaching the far side to a chorus of cheers from the exhausted engineers and sailors. This was the signal. The real flow of power could now begin. What happened next was one of the most decisive tactical maneuvers of the war in Europe. The lead elements of the 2nd Armored Division, hell on wheels, began their roll onto the bridge. The first Sherman tanks, then more, then the heavier Pershings, their massive treads clanking rhythmically on the steel deck, formed an endless, rumbling column. The bridge shuddered and flexed under the incredible weight, the anchor lines singing with tension. But Templeton's design, born from late-night calculations and stubborn faith, held firm. The column picked up pace. It was no longer a trickle. It was a torrent of steel. Truck after truck loaded with infantry, bulldozers, self-propelled artillery, and fuel tankers followed the tanks in a relentless, mechanized river flowing into the heart of Germany. The German defenders, who had been prepared for a slow, vulnerable buildup over several days, were completely overwhelmed. Their defensive plans, predicated on destroying slow-moving pontoon bridges, were rendered obsolete in a matter of hours. The speed and volume of the armored reinforcement pouring across Templeton's bridge was simply incomprehensible to them. Local counterattacks were crushed almost as soon as they were launched, overwhelmed by the sheer mass of American armor now on their side of the river. The strategic impact was immediate and total. The bridgehead, which German commanders had hoped to contain and destroy, exploded outward with unstoppable force. The Allied breakout from the Rhine had been achieved not in a week, but in a single day. The meticulous German defensive line east of the river collapsed into a state of rout and disarray. The road to the Ruhr, Germany's industrial heartland, was now wide open, and the Nazi war machine, already on its last legs, had suffered a mortal blow from which it could not recover. In that single, monumental day, Templeton's impossible bridge facilitated the crossing of over 8,000 vehicles and more than 35,000 troops, a rate of reinforcement that shattered all existing military records and fundamentally altered the endgame of the war in Europe. The experts who had predicted collapse were left to stare in stunned silence at the relentless column of power rolling across the Rhine, a living testament to the fact that sometimes the greatest obstacle to victory is not the enemy, but the limitations of conventional thinking. The success of the bridge was not just a momentary tactical victory. It was a strategic earthquake that reverberated through the entire German high command. Field Marshal Walter Model, one of Germany's most capable defensive commanders, had built his entire strategy on the assumption that the Rhine would halt the Allied advance for a critical week, if not longer. He planned to use that time to reorganize his shattered divisions, bring up reserves, and construct a deep defensive network east of the river. The reports that reached his headquarters on the morning of March 24th were initially dismissed as panic-induced fiction. A bridge made of ships, an entire armored division crossing in hours. It was impossible. But as the reports were confirmed by multiple, desperate sources, a profound sense of shock and dread set in. The Americans had not just crossed the Rhine, they had leaped over it with a force and speed that defied all military logic. Model's carefully laid plans were rendered useless before they could even be implemented. The initiative, already firmly in Allied hands, was now an unstoppable tidal wave. There would be no orderly retreat, no established defensive lines. The war had become a rout, and Templeton's bridge was the pivot upon which the entire Western Front turned. For Jack Templeton, standing on the western bank and watching the endless column of tanks and trucks rumble across his creation, the feeling was one of overwhelming exhaustion and sober vindication. There was no euphoric celebration, only a deep, quiet satisfaction that his theory had held under the most extreme conditions imaginable. He thought of the 4 engineers who had died on the deck of the Courage, and the dozens more who had been wounded. Their sacrifice was etched into the very steel of the bridge. He walked among his men, who were now collapsing into exhausted sleep wherever they could find a patch of ground, their faces blackened with soot and grime. He offered quiet words of thanks, a hand on a shoulder, a shared look of understanding that needed no words. They had done the impossible, not for glory, but because it was necessary. The skeptical senior engineers from SHAF, who had been present as observers, approached him. Their earlier disdain had been replaced by a stunned, professional respect. One of them, a full colonel who had been particularly vocal in his criticism, simply shook Templeton's hand and said, "I owe you an apology. Colonel, I have never been so happy to be so wrong." It was the only accolade Templeton truly cared about in that moment. The bridge, now officially designated Bridge No. 1, but forever known to the men as Templeton's Bridge, operated continuously for 72 hours before the first Bailey bridges could be completed nearby. It became the main artery for the entire U.S. Ninth Army's advance. The statistics compiled in the aftermath were staggering. In addition to the initial flood of troops and vehicles, the bridge supported the crossing of over 15,000 tons of ammunition, 250,000 gallons of fuel, and countless tons of food and medical supplies. It is estimated that the bridge's existence shortened the Rhine crossing operation by a critical 3 to 4 days, a time period in which the German army might have otherwise regrouped. Military historians would later conclude that this single innovation likely saved thousands of Allied lives and accelerated the end of the war in Europe by several weeks. The bridge was more than a piece of engineering, it was a war-winning weapon. As the front lines moved rapidly eastward, the bridge's purpose was served. It was eventually disassembled, the LSTs returning to their naval duties, the specialized components salvaged. Jack Templeton was awarded the Distinguished Service Medal for his extraordinary vision, technical skill, and determined leadership. He accepted the honor with his characteristic modesty, always insisting that the credit belonged to the men who built the bridge under fire. He returned to Nebraska after the war, shunning publicity and returning to his civilian work as a bridge engineer. He rarely spoke of his wartime experiences, and the story of his impossible bridge remained largely unknown outside of military history circles. For him, the true monument was not a medal or a footnote in a history book. It was the knowledge that his idea, born from a simple observation and forged in the crucible of combat, had helped bring thousands of soldiers home alive. He had looked at a fleet of ships and seen a bridge, and in doing so, he had helped build a path to peace. The legacy of Templeton's Bridge is a timeless lesson in the power of innovative thinking, the courage to challenge established doctrine, and the profound impact that one determined individual, armed with a better idea, can have on the course of history. It stands as a permanent testament to the truth that the word impossible is often just an invitation to try harder,